Pull a standard steel tape measure from its heavy plastic housing, and you will immediately see the familiar red marks measuring out 16 inches. But drag that cold steel blade just past the standard red numbers. Stop right at precisely 19.2 inches, and you will hit a solid black diamond. The untrained eye casually dismisses this tiny dark mark as a printing error, a manufacturing artifact, or some obscure metric conversion meant for another country. It is none of those things. The black diamond is an intentional, highly engineered feature. It is a critical marker designed specifically to manage the relentless physical forces acting upon the massive wooden frameworks that shelter us. That single, unassuming polygon is a geometric cheat code governing the structural integrity of modern architecture. We look at the towering skeleton of a massive residential building and see only a chaotic maze of raw wood. Walk onto any active, high-scale job site, and you will witness an industry built entirely around strict, unyielding dimensions. Standard building materials like heavy subflooring sheets, drywall panels, and exterior structural sheathing are all manufactured in rigid 8-foot lengths. That is exactly 96 inches of solid, unbroken mass that must be perfectly supported from below. For generations, contractors simply used solid, heavy lumber spaced every 16 inches to hold up this weight. But modern construction evolved rapidly. Builders shifted away from heavy, traditional lumber to lighter, highly efficient engineered I-joists. However, when these modern composite materials meet the old 16-inch spacing standard, a hidden physical friction begins to take hold. Sticking stubbornly to the old standard either wastes massive amounts of structural material or invites catastrophic deflection. What happens when new engineering principles simply ignore the fundamental geometry of physical space? Engineered I-joists are brilliant feats of modern manufacturing. They are designed to carry significantly heavier loads over much longer spans using far less raw wood. But this efficiency requires perfect load distribution. If you span a standard 96-inch sheet of subfloor across joists spaced at the traditional 16 inches, you create unnecessary structural overlap. The load becomes inefficiently dispersed across the framework. 6 joists end up carrying the weight that 5 could handle effortlessly. The materials are fundamentally mismatched, leading to a crowded subfloor where the geometry fights against the natural strength of the engineered wood. Watch closely as concentrated weight is dropped onto an unevenly supported span. The raw kinetic energy has absolutely nowhere to go. It travels straight down into the wood grain. You can physically see the fibers bowing downward, feeling the creeping threat of shear failure as the materials stretch beyond their ideal limits. The entire structure is fighting itself. It is buckling under the invisible weight of poor geometric alignment. The floor becomes vulnerable, bending slightly with every step because the structural supports are not catching the load at the optimum points of resistance. But divide a standard 96-inch span by exactly 5, and you arrive at a perfect 19.2. Observe the framing shift seamlessly to this new dimension. Watch builders stretch a vivid chalk line across the raw timber, snapping it down hard to mark exactly 19.2 inches. As the engineered joists are set precisely onto these new marks, the physical dynamic of the entire floor system completely transforms. 5 perfectly spaced bays now support the exact length of one sheet of subfloor. The edges of the wood meet precisely at the dead center of the joists. There is absolutely no overhang. There is no wasted timber cluttering the skeleton of the home. The architecture snaps into alignment. When the same heavy, concentrated load impacts this realigned surface, the kinetic energy is instantly neutralized. The invisible stress vectors stabilize. They distribute the heavy kinetic load evenly across the grain, turning the entire floor into a unified, This single point of equilibrium scales rapidly, transforming a sprawling landscape of ongoing construction. Look across the wide, skeletal frames of a massive housing development. When an entire neighborhood is constructed on the 19.2-inch standard, the compounding effects are staggering. Framing crews drastically reduce the total number of joists needed per individual floor. Thousands of linear feet of engineered lumber are saved across a single block of homes. Fewer joists mean less cutting, less heavy lifting, and fewer opportunities for structural failure. The entire development rises faster, leaning on a mathematical constant that ensures every single room is supported by an optimal grid of strength. It triggers a drastic reduction in material waste while exponentially increasing the structural safety of millions of square feet. You walk comfortably across your living room floor, never feeling a single vibration beneath your feet. That unbroken, solid silence is not a lucky accident. It is the direct physical result of that hidden geometric matrix locked away beneath the drywall and the hardwood. Every heavy piece of furniture, every running footstep, and every large gathering in your home is effortlessly supported by a web of precise alignment. The chaotic forces of gravity and kinetic motion are being silently managed by a measurement most people never even notice. Your reality remains perfectly stable because the architecture beneath it honors the exact laws of structural physics. Total architectural stability does not happen by chance. It relies entirely on an unassuming geometric constant, hiding quietly in the palm of every builder's hand.